Hello class, Professor Anderson here. Let's see if we can calculate the E field of a point charge, and let's do it using Gauss's law. So we know what a point charge looks like. Here's our point charge, let's call it positive Q. And that point charge has an E field that is pointing everywhere radially outward. And you'll see why I'm going to draw it with dashed lines in just a second. Okay, so there's the E field around my point charge plus Q. How do we calculate this E field using Gauss's law? What is the approach? Well, the first thing we do is we write down Gauss's law. So we know exactly what Gauss's law is. Gauss's law is the following. Integral E dot dA equals Q enclosed over epsilon naught. Once you write down Gauss's law, you need to draw a surface. So let's draw a surface around this thing. And since we have spherical symmetry, let's draw a sphere. And now you see why I drew it with a dashed line, because the E fields are inside until they poke out through the surface. So this is what I'm trying to represent here. E fields are inside this ball, and then they poke out through the surface. The left side of this thing is the total flux, right? This is the flux coming out of our closed surface. As Gauss said, it's proportional to the enclosed charge. So one thing that we can do right away is let's put a radius on this sphere. So we're going to say that this radius is r. Okay? You can draw any size sphere you want. Call it r in radius. We also need to think about dA. What is dA in this case? dA is a surface area element of the sphere. So if I think about the dA, it's a little slice of surface area that looks like that. Okay? But an area has a particular direction to it. And that direction is always perpendicular to the plane of that surface. So if you have a little piece of this sphere, dA is going out, which is good because we know that E is also pointing out, right? Everywhere E field is pointing radially outward, we can say E has a radial component that's exactly parallel to dA, and that's going to simplify this quite a bit. The other thing that we can say is E anywhere around on this sphere has to have the exact same magnitude. Why? Because it's always r away from the point charge. And by symmetry, if you flip the whole problem over, you have to get the same result, right? You have to get an E field that has the exact same strength over here as it would over on the other side. Okay, so what does this equation now become? Well, it becomes quite simply this. Integral of E dot dA becomes E times dA times cosine of the angle between them. All of that is equal to Q enclosed over epsilon naught. But we just said that E is a constant in magnitude around the whole thing, and so E can come right out of the integral. E integral dA. We also said that phi is the angle between E and dA, and that is 0 degrees, right? E is this way, dA is the same way, they're parallel. All right, this is looking good. It's going to simplify quite a bit. What does this whole left side become? Well, cosine of theta, cosine of phi, if it's 0, that thing becomes 1. And so we're just left with that. Over on the right side, Q enclosed is just positive Q, right? It's just one charge that's in there, positive Q, and so this becomes Q over epsilon naught. And now look at this right here. Integral of dA, closed surface integral. What does that mean? That is the area of the sphere, the surface area of the sphere, right? Pretty cool, because that whole thing just becomes 4 pi r squared. That's the surface area of a sphere. Equals q over epsilon naught. And now we are basically done. We just have to divide, and we get E is equal to 1 over 4 pi epsilon naught times q over r squared. And that's the electric field of a point charge. Now, you look at this answer and you say, okay, that looks right, except I don't have any direction there. Where do we get our direction from? The direction comes back from the symmetry in the problem. When we first wrote this down, we said the symmetry of the problem means the electric field has to be pointing radial. It's either radially out if it's a positive charge, it's radially in if it's a negative charge. In this case, we had a positive charge, and so we can get to our final result. You say E is 1 over 4 pi epsilon naught, q over r squared, r hat. Okay. Electric field of a point charge calculated using Gauss's law. All right, hopefully that's clear. Cheers.